Alright, in this video we'll take a look at problem number 7 from out of section 2.2, and this particular problem wants us to use the derivative formula, the definition of the derivative formula, to compute f prime of x, or to compute the derivative. This 2.1 and 2.2 here, if you look at our book, they're just referencing formulas. This is how they labeled two formulas in our book, and this is formula 2.2. So I'm going to use this formula, which the book labels as 2.2, to find f prime of x for this particular function. I realize that in this numerator I'm going to have to compute f of x plus h. F of x we already have, so that's not too bad. But I want to compute f of x plus h before I go into this formula. So f of x plus h, if this is f of x, I'm putting x plus h in place of this x in order to find the value here. So I'm looking at the 3 from the numerator, and in place of the x, I'm going to put x plus h. And the grouping symbols here I'm just using to denote that I put this quantity in place of that x. If it was like 2x in this denominator, the grouping symbols would be a little bit more important, because then we'd have to distribute that 2 in. So I always like to use them just to kind of show myself visually what I've put in place of x. And then if you have a coefficient on the x, they're definitely necessary, because then you'd have to do a distribution. But here they're just kind of visually showing me what I put in place of x, and then I still have the plus 1 in that denominator. And really this doesn't simplify very much, so I guess I could have gone straight to the formula with this. I just like to do it up front, because a lot of the time when you're computing this, especially if you have like an x squared or an x cubed, there's a significant amount of algebra that you can get out of the way right here before you go within the limit. Here we're kind of ready to go to the limit here. So f prime of x is going to be found by taking the limit as h approaches 0 of this expression, and I'm just going to drop the parentheses as I transfer this expression into the limit formula. So there's f of x plus h, there's the first component of my numerator, minus f of x. F of x would be, well, just 3 over x plus 1. And this is all over h. So this is kind of ugly. You don't really have any obvious cancellation that happens here. We're going to have to do a little bit of work to get to the point where something cancels, and the work that we're going to want to do is going to be to put these two separate fractions that we have within the numerator into a single fraction. So basically, to subtract two fractions, we would need to have a common denominator. If I multiply this denominator by that denominator, I'll have a common denominator. If I multiply the second denominator by the first, I'll have a common denominator. So what I'm going to do is I'm going to multiply this fraction by 1 in the form of x plus 1 over x plus 1. And I'm going to multiply the second denominator by 1 in the form of x plus h plus 1 over x plus h plus 1. Okay, so that basically will just leave me with a common denominator of x plus 1 times this quantity for each of the two denominators. Now in the numerator, what I can do is distribute the 3 into the two pieces here, and the sign of this 3 is technically negative, so I'm going to distribute a negative 3 into this. So my next line, I'm going to have a single fraction within this numerator. Common denominator is going to be x plus 1 times x plus h plus 1. All of this is still over the h in the bottom, so I still have a fraction within a fraction here, or a complex fraction. But in my numerator, I'm going to have 3 times x plus 3 times 1. So I'm going to have 3x plus 3, and then minus 3x, and then minus 3h, and then minus 3 times 1, so minus 3. And here's where the cancellation occurs that I told you will eventually happen. 3x, 3x, plus 3, minus 3. So all we're left with in that numerator is this minus 3h. Now if we look at this, it still doesn't look nice. I guess I'll rewrite it on a new line here. This still doesn't look nice at all, because we still have a fraction within a fraction, and usually in math that's something we try to avoid having happen. but we'll be able to address that on the next line. So we've simplified it to this. So we have that fraction in the numerator divided by h. When you're doing division with fractions, if you think of this fraction bar as representing division, you don't usually like to take one fraction and divide it by something. You'd rather multiply by the reciprocal of this. So rather than dividing this by h over 1, I'm going to multiply by 1 over h. This is going to be the limit as h approaches 0 of, I'm not taking the reciprocal of the big fraction I had up top. You're going to multiply by the reciprocal of what you were dividing by. So I'm going to multiply this by 1 over h. At this point, since this is all, since in the denominator this is all multiplication, and in the numerator it's also multiplication, I can cancel those h's. And what we'd end up with is we'd end up with the limit as h approaches 0 of -3 over x plus 1 times x plus h plus 1. All the other h's are gone, right? The other h is canceled back on this line. And now I think we're going to be in decent enough shape to plug 0 in place of the remaining h and get an acceptable value back. So if we go ahead and, oops, I don't need to do the limit anymore. I'm going to put 0 in place of this h. If I put 0 in place of that h, I'd be left with a -3 in the top. There's no h on that, so that's staying as an x plus 1. I'd have x plus 0 plus 1, or just an x plus 1 here. So this is f prime of x. So here's the derivative of the function that we started out with. In about a week and a half, we'll have a little quicker way to take this derivative, but to use the definition of the derivative, to use this, the definition of the derivative to find f prime, this is basically what you'd have to go through.